Let's look at trigonometric exponentials and their relationship with trigonometric functions, or complex exponentials and their relationship to trigonometric formulas. We are assuming that we are comfortable with Euler's formula, which is e to the jx is equal to cosine x plus j sine x. That's Euler. And if you wanted to remind yourself what that is saying, or one way of viewing that, you could say, well, what's the magnitude of e to the jx? That's just the magnitude of this real number plus j imaginary number, or that's now the square root of the real part squared plus the imaginary part squared, and we know what sine squared plus cosine squared is. That's equal to 1, and the square root of 1 is 1. The magnitude then of e to the jx is 1. The angle of e to the jx is just the inverse tangent of the imaginary part over the real part. The imaginary part is sine of x. The real part is cosine of x. But that's just the inverse tangent of the tangent of x, which, if we take the inverse tangent of the tangent of x, or the tangent of an angle, and then take its inverse tangent, that will just give us x. And so the angle of e to the jx is x, or e to the jx you can think of as this rotating phasor that's mapping out the unit circle, where we've just now concluded that the length of that is 1, the angle of that is x, and if we wanted to find this particular value, this is simply the real part of that, which is cosine of the angle, which is cosine of x, and this vertical distance is just the sine of that angle, which is sine of x. And now we have a real part for this complex number e to the jx. We have the real part, cosine of x, and the imaginary part in the vertical direction plus sine x. Let's use Euler to derive some of these sum of angle formulas for sine and cosine, and once you've seen this for one, you can hopefully believe how you can derive that for another, meaning you don't have to have all of this memorized. You can actually derive these at your leisure on some beach sometime, so that you now can have fun with your complex exponential. Here's e to the j times a plus, or e to the j of a plus b, and we could view a plus b as the sum of two angles. That by Euler is just cosine of the argument, which is a plus b, plus j sine of the argument, a plus b. What we're wanting to do, though, is remember that we can express e to the j times a plus b as this product of complex exponentials using the exponential relationship that we know to be true, and now simply expand e to the ja using Euler and e to the jb using Euler, giving us cosine a plus j sine a times cosine b plus j sine b. If we multiply all of this out and look at the real part will just be what is cosine of a plus b, and the imaginary part will be simply sine of a plus b. If we multiply this product of terms out, we're going to have this piece, and so that's going to be cosine a times cosine b. And hopefully you can see that when we multiply j sine b times j sine of a, the j's become j squared, that's just minus 1, and we now have minus sine of A sine of B. That is just 2 of the 4 product terms. We can now look at cosine of A times J sine of B, and that's scaled by J, so that we now have J cosine of A sine of B, and we also have remaining this additional piece, which is going to be J sine of A times cosine of B, and again that gets multiplied by J, so that we now have plus sine of A cosine of B. This is then the real part, or we now can conclude that the cosine of A plus B is equal to, or we've just derived that that's cosine A cosine B minus sine A sine B, and we've also shown that the sine of this sum of A plus B angle is cosine A times sine of B plus sine of A cosine of B. And hopefully you can see that if you wanted to get the difference of two angles, you could simply replace that with the minus sign in these formulas, and then you have this being the minus JB, and subsequently you could derive those expressions like similarly to how we have derived this sum of two angle expression.